What if I told you that the only difference between the beautiful resonant sound of a grand piano and like that harsh digital alarm clock beep that wakes you up every morning is basically just a single negative math constant?
I mean, it really is the ultimate magic trick of the universe. We're taking something that looks incredibly sterile and, intimidating on a chalkboard, and we're watching it literally burst into physical sound.
It's wild. So let's imagine you are holding a guitar. You're looking at a single taut string. It is stretched incredibly tightly between two fixed structural bridges. So you've got the nut at the top of the neck and the saddle down on the body of the guitar.
And to understand what happens when you play that string, we just need to track two very basic dimensions. First, you have your horizontal position along the string. We'll call that space, or, your position from left to right. It starts at the left bridge and it ends at the right bridge. Simple enough.
Right.
But the string doesn't just sit there. When you play it, it moves up and down. That vertical stretching, the actual vibration up and down, that is our displacement.
And that up and down movement is where the absolute chaos begins, mathematically speaking.
Oh, yeah.
Because that vertical movement depends on two totally different things at the exact same time. If I want to know exactly where a microscopic piece of that string is in space, I need to know where I am looking along the neck of the guitar. And I need to know the exact millisecond in time that I'm looking at it.
Right. Which is the inciting incident of our whole physics problem. You pluck the string with a pick, or say a felt hammer strikes it inside a piano.
You deform its natural shape.
Exactly. You pull it away from its resting state. And the second you let go, the mechanical tension pulling horizontally along that string, it desperately tries to drag it back to a perfectly straight, flat line.
And that violent tug of war is what the classical 1D wave equation is actually measuring.
Here.
When you look at the master equation in the source material, it looks like a nightmare of calculus.
Yeah, it really does.
You've got second derivatives of space on one side, second derivatives of time on the other, all linked together, but it's actually telling a very intuitive story.
Yeah, if you strip away the Greek letters, the right side of that master equation is simply tracking the physical curvature of the string.
Curvature.
Right. It is literally measuring how sharply the string is bent at any microscopic spot.
Yeah.
And then the left side of the equation is tracking the physical acceleration. So the literal force pushing that specific tiny piece of the string up or down.
Think about it like a stretched rubber band.
Oh, I love this analogy.
Yeah, like if you pull a thick rubber band and just bend it gently so you have a really wide, shallow curve, and then you let go, it snaps back, but it does so somewhat slowly. The acceleration is low. But if you take your fingernail and pinch that rubber band into a really sharp, extreme V-shape angle, and then release it, it accelerates back with violent, blistering force. It'll, like, snap your finger.
That is a brilliant way to visualize it. The sharper the physical bend in the material, the harder and faster the universe pulls it back to equilibrium.
Wow.
And the equation simply links those two realities. Curvature dictates acceleration, and they are linked by a specific constant multiplier, which represents the wave's speed.
And that speed is dictated entirely by how tight you've tuned the string and how thick and heavy the material is.
Which is why a thick, heavy bass string vibrates so much slower than like a thin, high-tension violin string. The math is just tracking that rubber band snap.
But here's where my brain starts to hurt. We have this master equation linking curvature and acceleration, but the string is changing its physical shape in space, and it's simultaneously moving and evolving over time.
Yeah, that's a lot.
How on earth do you solve a math problem that is essentially a moving target in two different dimensions at once?
You don't. At least not all at once. To solve this without drowning in an impossible calculus loop, mathematicians use a technique called the method of separation of variables.
Separation of variables. Okay.
It's basically a strategic hack. We essentially assume that we can take the spatial shape of the string and its time-dependent rhythmic vibration and split them completely apart into two isolated buckets.
Wait, I'm trying to visualize that. You're saying we take this chaotic, moving, vibrating wave and essentially freeze it.
Kind of, yeah.
We force space and time to divorce each other.
Yeah.
It's almost like taking a movie file and splitting it into a separate audio track and a separate video track so you can edit them independently.
Yes, you separate the tracks entirely. If we connect this to the bigger picture, this is the master key to advanced physics. You turn one impossible multivariable problem into two very basic, ordinary equations.
They make so much sense.
Right. You create a pure space bucket that only cares about the geometric shape of the string, and a pure time bucket that only cares about the ticking of the clock.
So we take those isolated buckets, we run them through our rubber band equation, and we basically reorganize the furniture. We divide everything out so that all the time variables are sitting exclusively on the left side of the equal sign.
Yep.
And all the space variables are sitting exclusively on the right side.
Which leaves us with a massive logical paradox. This raises a really important question.
Uh-oh.
You have a fraction on the left that is changing strictly as time ticks forward.
Okay.
You have a fraction on the right that is changing strictly as you move along the physical length of the string.
Yeah.
How can a formula that is only changing based on a clock always be exactly equal to a formula that is only changing based on physical distance?
Wait, I don't get it. They're completely independent.
Exactly.
If I move 2 inches down the guitar string, the space side of the equation changes, But the time side doesn't know I moved. So how can there still be an equal sign between them? That shouldn't be possible.
It's a total contradiction. Well, unless you make one massive logical deduction. The only mathematical way that works, the only way the time track and the space track can always equal each other no matter what coordinates you plug in, is if they are both secretly locked to a shared fixed permanent number.
A constant value.
Yes.
Oh,
okay.
Because if the time bucket always equals the number 5 and the space bucket always equals the number 5, then they always equal each other.
Yeah.
The variables can dance around all they want, but the whole fraction is anchored to a permanent rock.
Precisely. We call this anchor the separation constant. The source material labels it with the Greek letter lambda.
Okay, lambda.
So now, instead of one terrifying multivariable equation, we have two very manageable equations. We have our spatial curvature equation, and it equals lambda. And we have our time acceleration equation, and it also equals lambda.
Okay, we successfully hacked the equation. We've split the tracks.
Yeah.
But we have a glaring new problem here. We just invented this constant lambda to make the math work.
Right.
We don't actually know what number it is. It's just a blank placeholder.
Yeah.
How do we figure out what lambda actually represents in the real physical world?
We deduce it by testing it against reality. And by reality, I mean the boundary conditions.
The bridges.
Remember those fixed structural bridges we talked about? The nut and the saddle of the guitar? The string is rigidly clamped to those pieces of wood or metal.
Right.
Therefore, the vertical movement of the string at those exact edges can never, ever be anything other than zero.
Right, because if the string is moving at the bridge, your guitar is broken.
Right.
The ends are tied down tight.
Exactly. So we have to find this mystery constant lambda. Let's test it out. What happens if we assume this constant is a positive number, a number greater than zero?
Okay, let's try positive.
If you plug a positive constant into the calculus, it yields an equation for real exponential growth.
But wait, wouldn't exponential growth just mean the string gets louder and louder? Like cranking a concert amplifier up to the maximum volume?
That's what your intuition wants to say, but physically, no. If the shape of the string followed exponential growth, it would mean the string bows outward, stretching further and further into space infinitely.
Oh, wow.
Yeah, until the material violently snaps. But even mathematically, it fails. Because if you take an exponential growth curve and you force the two ends of it to be pinned down at zero because of our bridges, the only way the algebra survives is by collapsing completely. All the coefficients become zero.
Meaning the string isn't vibrating at all.
Right. It results in a perfectly flat, dead, silent string. So, a positive value for our mystery constant is mathematically and physically rejected.
Okay, so no infinite snapping strings, process of elimination. What if the constant is exactly zero?
Well, if the constant is zero, the calculus simplifies the string's shape into a perfectly straight line.
Okay.
But again, you have to angle that straight line so that it hits zero at the left bridge and exactly zero at the right bridge. The only straight line that can physically cross both those 0 points simultaneously is a completely horizontal line lying flat against the fretboard.
Another dead silent string. So positive is out, zero is out. By pure process of elimination, the physical universe forces this mystery constant to be a strictly negative number.
It is the only survivor. And this is where the magic happens. When you plug a negative constant into our spatial equation, it transforms into something physicists absolutely love, a classic harmonic oscillator.
A harmonic oscillator. That's the math of things bouncing back and forth smoothly, right? Like pendulum, springs, waves, sines, and cosines.
Exactly. A negative constant means the solution for the string shape is a combination of standard wavy sines and cosines. But we still have to apply our physical bridges to these wavy shapes to see what actually survives.
Right.
Let's start with the left bridge at our starting position of zero.
Okay, so the string is clamped down, displacement is zero.
Now, think about how a cosine wave naturally behaves. A cosine wave natively starts its cycle at its absolute maximum peak. It starts at a value of 1, but our physical bridge demands that the string starts at a value of 0.
Wait, you're saying the math just throws the entire cosine wave in the trash? You can't just erase half of an equation because it's inconvenient.
You can when the physical world demands it. Because it is physically impossible for a wave that starts at a peak to represent a string that is clamped down to 0, the coefficient for the cosine term is forced to be 0. The math literally squashes the cosine wave out of existence. We are left with pure, clean sine waves simply because we clamped down the left side of the string.
That is wild. The physical clamp dictates the surviving math. But we still have the right bridge at the other end of the guitar. We have to clamp that down too.
We do. We have our surviving sine wave stretching across the guitar, but it has to perfectly hit a value of 0 right where the second piece of wood is located.
Right.
Now, we can't just set the coefficient to 0 again, or we'd erase the sine wave too, leaving us with another dead string.
So if we can't squash the amplitude to 0, how do we force the wave to meet the bridge? Does the wave itself just have to perfectly cross the center line right at that exact spot?
Yes. The sine wave naturally rises and falls, crossing the 0 line at very specific intervals. It crosses 0 at pi, at 2 pi, at 3 pi, and so on. Regular integer intervals.
Okay.
This means that whatever is happening inside our sine wave, by the time it reaches the end of the string, it must perfectly equal a whole integer multiple of pi.
Oh, I see where this is going. Because of that right-hand bridge, our mystery constant can't just be any random negative number. The separation constant is locked. It is confined into rigid, specific, perfectly measured harmonic levels. One big loop, or two perfect smaller loops, or three perfect smaller loops.
The rigid boundaries literally demand it. If a wave tries to vibrate at, say, 1.5 loops, it misses the bridge, the math breaks, and the physics won't allow it to sustain. The bridges force the continuous, chaotic possibilities of the universe into discrete, perfect integer steps.
The boundaries are what create the structure. That is amazing. So we finally deduced the physical shape of the string. We have these perfect spatial sine waves frozen in space, but we still have an unfinished movie. We only have the video track. Music isn't a frozen shape, it's a dynamic, moving experience. We have to go back and get our time bucket and merge the tracks back together.
We do. We take that valid negative constant, the one we just proved is locked into integer multiples of pi, and we plug it back into our isolated time equation. Now, to make the physical reality clear here, we define a new concept, the fundamental angular frequency.
The frequency. So we're talking about how incredibly fast this shape is bouncing up and down.
Right. And this frequency is dictated by the wave speed, divided by the length of the string, multiplied by those perfect integer loops. When you merge this frequency into the time equation, it perfectly mimics our harmonic bouncing. It tracks an ongoing rhythmic back and forth oscillation over time.
So the space bucket gave us a wavy shape perfectly clamped between the bridges, and the time bucket tells us how violently and quickly that specific shape is rhythmically blurring up and down.
Exactly. And step 4 in the source material is assembling the complete superposition. We multiply our spatial standing wave loops against our rhythmic time bouncing tracks.
Okay, that makes sense.
But if we stop there, we are missing a crucial, beautiful reality. A real piano string or guitar string doesn't just vibrate in one single simple loop.
Right. Because if you film a plucked string in slow motion, it's not just one clean jump rope. It's vibrating in one big fundamental loop spanning the whole length, but it's simultaneously vibrating in halves and in thirds and in quarters. All those perfect integer harmonics are overlapping, bouncing around at the exact same time. It's a chaotic mess of perfect math.
It is. And to capture that reality, physicists use the principle of superposition. We don't just take one solution. We literally sum up every single valid integer harmonic mode, from the first fundamental loop all the way to an infinite number of microscopic loops. We add them all together into one massive stacked equation.
Here's where it gets really interesting. I like to think of this principle of superposition, like taking a bite out of an incredibly complex dish prepared by a Michelin star chef.
Oh, that's a great way to put it.
When you take a bite, you don't taste the sea salt, and then 3 seconds later taste the brown butter, and then later taste the roasted garlic sequentially. You taste an infinite simultaneous combination of distinct ingredients hitting your palate all at the exact same moment to create a single unified flavor.
What's fascinating here is that this infinite sum, this superposition of layered ingredients, is exactly what gives an instrument its unique voice, its timbre. Why does a guitar sound like a guitar and a violin sound like a violin, even if they play the exact same note?
It's the recipe.
Right. It's because the physical material, the stiffness of the steel versus the friction of the bow, dictates the exact recipe of how those infinite overlapping waves sum together.
So going back to what we said at the very beginning of the deep dive, the reason a piano playing middle C sounds so rich, warm, and emotional, while a computer's digital beep playing middle C sounds harsh, flat, and annoying, is because the piano physically possesses all those infinite, overlapping integer waves perfectly stacked on top of each other.
Exactly.
The digital beep just has one single, lonely wave.
The math of superposition is the literal recipe for a piano's warmth.
I love that. We have literally built the entire mathematical universe of a vibrating string from scratch, just by applying logic to a rubber band and 2 wooden bridges.
We really have.
But if you are listening to this right now because you are staring down a physics or calculus exam tomorrow morning, everything we just talked about actually gives you a massive shortcut.
If an exam problem states that displacement is 0 at the edge, meaning the physical object is clamped or tied down, you can confidently use a pure sine series right from the start. You don't even need to write the cosine out.
That's a huge time saver.
However, if you encounter a problem with a different boundary, say a 0 slope, or a thermally insulated boundary where things aren't clamped to 0, you use a cosine series instead.
So clamped to 0 displacement equals sine series.
Yep.
Insulated or 0 slope equals cosine series. Just knowing the physical reason behind that instantly lets you skip like 5 lines of tedious algebra.
Precisely.
We started out talking about a terrifying calculus equation, but realized it's just telling a story about a rubber band.
Yeah.
The sharp, physical bends of a guitar string dictate its extreme acceleration, forcing it to violently snap back.
Right.
We saw how mathematicians pull off an incredible trick isolating space and time into totally separate tracks to figure out how that string moves. And most beautifully, we saw how simply clamping a piece of wire down to 2 wooden bridges forces the endless possibilities of the universe into discrete, perfect mathematical harmonics.